So here's our review. So the kind of problems we're going to do is we're going to find the absolute extrema for a function inside an interval. And we're going to say that interval is from x equals a to x equals b. So we've kind of gotten used to finding critical numbers and using the first derivative test and so forth. This is actually stepping back to the first section. So you can look at some of the homework problems that were like that. The key thing is the steps are you're going to find the critical numbers. And I'm going to be nice to you guys. I'm just going to give you polynomials. So basically, to find the critical numbers, you find the f prime of x. So you do that using calculus, using the appropriate power rule formulas. You set the first derivative, so you find the first derivative of some equation. And then you set the first derivative equal to 0. Now, theoretically, you'd also have to consider the places where the derivative equals 0, but in this case, because it's polynomials, not 0, but undefined. So in this case, it's just finding where it's 0. So, you're going to end up with a x squared plus something, and you're going to factor it. So this involves factoring, and that'll give you the x values. And again, typically, because if I do a, say, original function's a fourth order polynomial, the derivative's a third order polynomial, that would be hard to factor and take time. So typically the function is a third order polynomial and the derivative is a second order polynomial, a quadratic, which then you can factor easily. So what factoring is going to give you is, x equals critical number 1 and x equals critical number 2. Those are the possible points of minimum or maximum. So for this problem, which is not your first problem on the test, but it's in there, is you're going to evaluate the function at 4 places. You're going to evaluate the function at the value of x, which is the beginning of the interval. You'll get that. You'll evaluate the function at the end of the interval. You'll get that. You'll evaluate the function at the first critical number, and you'll evaluate the function at the second critical number. So you'll have 4 numbers. And let's just say this one is negative 20, this is 5, this is negative 10, and this is 25. Okay, so these are the values you get by plugging these x values into the original function, okay, not into the derivative, because if you do that, you'll get 0 for the derivatives for these things. You plug it back into the original function. And then you look at those 4 numbers, and you look for the most negative, or the one that's that's most negative. If you put it on a number line, it's the one that's most to the left. So this is the most negative. Negative 20 is more negative than any other number. So this is going to, the most negative is what we call the absolute minimum for that. And the most positive is this one down here. Most positive, not post, most positive. And the most positive number is going to be your absolute maximum. So when you have an interval and you have a function, the maximums and minimums can either occur at the critical numbers or they can occur at the beginning or end of the interval. And that's why you have to evaluate the function at those 4 points to find out which one is the most negative. That's the minimum, most positive. Excellent. Okay, I'm not going to work through a problem. You can look in the homework. Now the next problem is where you fill out the tables and you look at the first derivative test. So I'm going to start with some polynomial, and it's going to be a third order polynomial just because otherwise it's not too exciting. It's exciting enough, but not too exciting. So usually what I do is I start with the derivative and then I integrate it, now that we know about integration, and find the antiderivative that works out so that the roots are reasonable. Actually, I think in this case, for this problem, I think I did it so that the roots are not so nice. You're going to have to use completing the square or the quadratic formula to find the roots. So make sure you write the quadratic formula down, which says x is equal to minus b plus or minus the square root of b squared minus 4ac over 2a. So you might have to use that here to find this. I'll let you know on Thursday, but make sure you have that on your paper. For this one, I'm going to make sure that it does have nice roots. So if you don't get nice roots, you've done something wrong. So you're either going to be given a function that looks something like this. And I'm just making these up, so I'm not going to actually use them. So you'll either have where the first term is positive or the first term is negative. And the reason I am choosing these two examples is to make a point. So in both of these cases, you're going to end up with two critical numbers, because when you take the derivative of this, you'll end up with x squared. And when you take the derivative of this, you'll end up with x squared. The key thing to remember is if you have a negative sign here, what that means is you're going to have a third order equation that looks something like this. Whereas if you have the positive first term, it's going to look something like that. So notice that here we have the maximum first and then the minimum. Here we're going to have the minimum first and then the maximum. So when you take the derivative of this and you evaluate use the first derivative test, or you take the second derivative, you've got to make sure you don't simplify anything when you look at the first and second derivatives, that you don't divide by -1 to get rid of that sign. That sign has to stay intact. So I'm just going to pause for a second because I'm going to make up one that's not on the test, but I'm going to show you both of these. So I've come up with one, hopefully I did this correctly. So we have 4x cubed, so f of x equals 4x cubed minus 72x squared plus 420x plus 120. Okay. So when you're solving these, what we're looking for is the critical numbers, whether those are maximums or minimums, and then also use the both first and second derivative tests to determine whether the critical numbers are maximums or minimums. So we'll just go through the whole thing and demonstrate this. So if I take the derivative of this, I'll end up with 12x squared minus 144x plus 420. So that's the derivative. Then what you do is you set the first derivative equal to 0. Now to solve for the roots, you can divide by 12. So we can, for finding the critical numbers, we can divide everything by 12. So you'll end up with x squared minus 12. And let's see, 420 divided by 12, I think it's 35, based on what I remember. So let's do that. 420 divided by 12 is 35. Okay, so I'll get negative 12x plus 35 equals 0, and I can factor that as such. So my critical numbers are x equals 7 and x equals 5. These are the values of x where I might have a maximum or minimum. Now I'm just going to add another page here. What if my original function was negative 4x cubed plus 72x squared minus 420x minus 120. So the only difference is when I take the derivative, everything's going to be negative. I'm going to have negative 12x squared plus 144x minus 420. Let's set that equal to 0. I can divide by through negative 12. Okay, so if I divide by negative 12, I'll end up with the same equation to factor. And I'll get the same answers, x equals 7, x equals 5. The difference is one of these is going to be, say this one's going to be a maximum, this is going to be a minimum. No, actually this is going to be a maximum, this will be a minimum. In this case, it's the opposite way around. They flip which one's max and minimum because of the reason I said earlier. So when you have to go back and evaluate the sign of the first derivative, you don't want to use this equation. You don't want to use the simplified equation that you use to factor to find the critical numbers. You want to use this one. Or at least if you do use a simplified version, that you do the one, you make sure you maintain the negative sign. Okay. So that's very important. So now we're going to use the first derivative test. I'm going to give you the tables that you can fill in to find out whether okay, so the first derivative test is going to tell us whether these critical numbers are minimums and maximums. We need to make up a table that's 4 by 4, and that'll be on your test sheet. So the way these are filled out, and some people get them wrong, and because it's 4 by 4 in this case, it works out okay, but just for uniformity, I hope that you fill them in this way. The reason it gets confusing is because when you do the sketching, it goes the other direction. So our interval in this case is going to be from negative infinity to our least positive critical number, and then between the two critical numbers, and then from the highest to infinity. So that covers all real numbers. We pick a value of x in these intervals to evaluate the derivative. We want the sign of the first derivative. We don't really care what the value is. And then we have our comments, which is relating to increasing or decreasing.
Okay, so now that we've found the critical numbers, we have to set up our first derivative test. So we need to choose values that are inside these 3 intervals. So the first one we look for is where is 0 in these intervals? Well, 0 is from negative infinity to 5. 6 is between 5 and 7, and 8 is greater than 7. So those are the 3 values of x that we have. Then we're going to evaluate the derivative at those values of x. So the easiest one is 0. And we go back to the derivative of the function. Here we simplified it by dividing by 12, but we want to go back to here before we do any kind of factoring out. And that's because this form has the appropriate signs that will tell us whether it's about its end behavior. So because we have a positive 12 here, we know that the function is going to start out like that and then maybe loop around and go back up. If this were negative 12, it would go the other way. So we got to make sure that we haven't taken that information out. So here we are. So you can see the answer is 420, which is positive. Now we know from our previous experience, this is going to be negative and this will be positive. But I want you to go ahead and calculate the values at those values of x. So we've got 12 times 6 squared minus 144 times 6 plus 420. And we already know that should be negative. But let's see what it actually is. And something is wrong. So let me just pause for a second. Okay, I just put a number wrong in my calculator. So I get negative 12, which is negative. And then if I do f prime of 8, I get 12 times 8 squared minus 144 times 8 plus 420. So I put that in the calculator. And I get 36, which is positive. So from this, I know this is increasing. This is decreasing. This is increasing. And so I'm going from increasing to decreasing. Here I'm going from decreasing to increasing. So if I want to use the first derivative test, I can say we have a local maximum at x equals 5 because we change from increasing to decreasing. And we can do the same thing. We have a local minimum at x equals 7 because we change from decreasing to increasing. So that's the first derivative test written out. So it goes from an increasing function to a decreasing function. Like over here, then we have a maximum. If it goes from decreasing to increasing, then we have the local minimum. Okay, the next step is to use the second derivative test. So what we would do is we would go back here and we would take the second derivative. So the second derivative of f of x, we just go to the first derivative and do it again. So we get 24x minus 144. So that's the second derivative. If we set that equal to 0 and solve for x, we will get possible points of inflection. So we have 144 over 24, and it should be 6 because it's halfway between the two critical numbers. Okay, so x equals 6 is a possible point of inflection. We don't know its a point of inflection until we've made our table up using the second derivative test. So we have the same size except one less column because we only have 2 intervals instead of 3 intervals. So we have our intervals. We have our x value. We have the sign of the second derivative. We have our comment. So we go from negative infinity to the possible point of inflection, and that possible point of inflection to positive infinity. Again, we pick x values. The easiest one is 0 here, and 7 would be the next integer greater than 6. So you evaluate the second derivative at these 2 values of x. So we go back to here. Second derivative is 24x minus 144. So this is going to be negative 144 because when you plug x equals 0 in, you just get the constant at the end. And we know from past experience that this should be positive, but let's just double check. So we get 24 times 7 minus 144. Which is 24. So that's positive. And as far as filling out the table, this says concave down. This says concave up. So concave down is like that, and concave up is like that. So what can we say about the results of this second derivative test? Well, we can now say that we do have a point of inflection. So we can say we have a point of inflection at x equals 6 because our function changes concavity there. Now it doesn't have to go from up to down or down to up, it just has to go from one or the other. In this case it goes from concave down to concave up. So that is the conclusion we can make about concavity. Now as far as the minimums or maximums, you can see from this drawing that our critical numbers, x equals 5 is in this interval, and x equals 7 is in this interval. So in the interval where we have x equals 5, it's concave down. So the second derivative test would say, since the function is concave down at our critical number x equals 5, we have a local maximum there. And then we could say the same thing for the other one. We could say since the function is concave up at our critical number x equals 7, we have a local minimum there. And if we go back to our first derivative test, which I think somewhere here, I guess it's over here, we came to the same conclusion. Using the first derivative test, because it went from increasing to decreasing, we had a local maximum at x equals 5, and because it went from decreasing to increasing at x equals 7, we had a local minimum there. That's exactly what we got using the second derivative tests.
We're going to have two optimization problems. One is going to be like problems, the first ones we worked in class. So I'm going to just reference those, and I'm not going to work out any additional problems. You can just look at the ones that we did in class and that you had for homework. And if you don't understand them, you can come and ask me about them. So problems 3 through 8. So if you want to practice more, this is on page 223. So it's going to be one like that. So you have to look at the equation, look at the description, and determine which is the primary equation, which one's the secondary equation. So there's going to be something involving a product. So if they say maximize the product, then you'll use this equation as your primary equation. If they say the product is 100, then you're going to use this as the secondary equation. So if the product equals a number, it's a secondary equation. If we're maximizing or minimizing the product, then we use this as our primary equation. The second equation is the sum, and you just have to figure out what the equation is, basically. So again, if they give you what the sum is, then that's the secondary equation. If they say to maximize or minimize the sum, then you're going to use that as the primary equation. So you have all those options in you can look at the odd numbers and look at the homework. The second optimization problem is going to be fairly straightforward, and I'm going to reference you to problems 19 and 20 on page 223 and 224. They're fence problems. So, there's two things associated with a fence. There is an area, and then there is a length. So I'm just going to demonstrate this. I'm not going to solve the problem. You have one of these for your homework problems. So you've got 3 corrals here, and the area, and if you give the dimensions for the height and the width of the corral, each one of these is going to be the same width. So the total width here is going to be 3x, and the total height is y. So if you want the area, it's going to be 3y times 3x times y. Now the total amount of fence is going to be x. You're going to have these 3 parts, which should be 6x, and then you're going to have 1, 2, 3, 4 y's. So one equation is the area, and the other one is the length of the fencing. And I'm not going to write these out. You're going to have to think about it. So depending upon what is, you read the problem and you're going to ask the question, what am I trying to minimize or maximize? Am I trying to minimize the length of the wire, or am I trying to maximize or minimize, probably maximize the area? You probably want to minimize the length or maximize the area. Otherwise, you would be wasting money. So one's going to be a primary equation, one's going to be a secondary equation. You're going to use the secondary equation, use substitution to rewrite the other one in terms of one variable. Then take the derivative, set the derivative equal to 0. Solve for the values of x or y, depending upon which way you go, how you substitute. That make the first derivative 0. Once you know the value of x or y that makes the first derivative go to 0, then you plug it back in to the secondary equation to get the other unknown, so you get both dimensions. So, like I said, I'm not going to work through the problem. Otherwise, I'd be showing you the exact answer. So, you have this case where you've got all sides of the fence. You also have, if you look at problem 19, there was the case where there was a river, and then you created these hens, and the difference with this one was that you didn't need fencing on the riverside. So the area would still be x times y, or actually in this case y. If you have three parts, you'd have the area would still be equal to y times 3x, but the length of wire, you don't need these three. So this would be, the length of the wire would be 3x plus 4y. Here you have 6x plus 4y for the length. Okay, so those two optimization problems. Horizontal asymptotes. So what I'm looking for here is just answering the question, what is the limit as x goes to infinity of some ratio, some rational function? You know, you might have x cubed over 4x cubed plus, you know, the other terms, whatever those are. When they have the same highest order term, x cubed, here it's just the ratio of the leading coefficients. If you have, let's say, x squared plus the lower order terms, and here you have x cubed, even if it doesn't really matter what the constant in front of it is, that's always going to be 0, because this term is going to become insignificant relative to this term when you get x getting to be very large. And the third case is where you have the numerator have a higher order term here, and in this case the limit does not exist or approaches infinity. So those are the three choices. Just have to recognize which one there is. It's either going to be 0, some number, or the limit does not exist. And then the final problem involves calculating the slant asymptote. And you know, this is the kind of equation where you need a slant asymptote, where the numerator is a higher order than the denominator. So we did this in, I think, class. Long division. Make sure you can do long polynomial division. So you have, you know, x squared plus blah 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 here, and you have, you know, 4x cubed plus the other terms, and ultimately what you'll end up with is something like x plus 5 here. I don't know what it is, actually be 4x because I need to multiply this out. Whatever you end up here is your equation. So you want to put the equation down. The remainder goes to 0 when x goes to infinity. So when you get x large, positive or negative, the equation simplifies down to this linear thing. So that's what I'm looking for. I'm looking for the equation. So don't just do the division and then just say, assume that I know what's going on here. I want to see y equals 4x plus 5. I want the actual equation of the slant asymptote. Okay. I think that pretty much covers it. So we've got finding the absolute extrema on an interval, find the critical numbers, evaluate the function of the critical numbers plus the beginning and end of the interval, find out which is the most positive and most negative. So give you the absolute extrema. The second one is taking a third order polynomial, finding the critical numbers, setting up your table for the first derivative test, showing that whether the values of x, which are the critical numbers, are local minimum or maximum, and you can do that by looking at whether it changes from increasing to decreasing or decreasing to increasing. Make sure you evaluate the functions at these three, even though you might be able to figure out exactly what the order of these is once you know it. You always want to use one of them is going to be 0. That's always the easiest one. Then you're going to answer some questions about concavity by taking the second derivative, setting that equal to 0, finding the values of x where the second derivative is 0. You You create another table using this as your thing that breaks apart the interval. Pick numbers inside these intervals. Evaluate the value of the second derivative at these values of x. And if it's negative value, then you know it's concave down. If it's positive, it's concave up. Then you can use that information to go back and check what you did for the first derivative test. You're going to look at the critical numbers, see which intervals those are in, and see whether it's concave up or concave down. If it's concave down, then it's a minimum, a maximum. If it's concave up, it's a minimum. Then you have your optimization problems, which are number problem and the fence problem. And then you're going to use the rules for horizontal asymptotes, and you're going to calculate the slant asymptote. So that's pretty much it. It's pretty straightforward. So I think you should be able to do well on it.